what exactly is light? I mean, it's one of those words we use every single day, but if you stop and, genuinely think about it, the reality is just so much stranger than those simple diagrams we learned in high school.
Oh, absolutely.
We know it acts as both a wave and a particle, a photon at the same time. And maybe the most mind-boggling thing for me is that the visible light we see, the stuff we rely on, is this impossibly narrow, tiny slice of a huge spectrum.
And that's the core paradox we're going to get into today. We've pulled together a whole stack of sources for this one, everything from casual science discussions and historical papers all the way up to some pretty advanced optics textbooks.
Okay.
So our mission for this deep dive is to take these fundamental and yet sometimes very mathematical concepts about the physics of light and just distill them into core insights about the universe you can actually see and interact with.
So, for you, our listener, this is really the ultimate shortcut. We're going to try and master the structure of the entire spectrum, understand that surprising atomic dance that causes everything from the color of your shirt to, I don't know, refraction in a lens.
Right, and even appreciate the powerful mathematics physicists have to use just to wrangle waves.
We're moving way beyond what color is this and into the deep mechanics of why a fiber optic cable works or why the speed of light is, well, only a limit in certain contexts.
Let's start with that grand unified theory of light.
Okay, let's unpack this. When physicists use the word light, are they only talking about that tiny visible part of the spectrum? Or is all electromagnetic radiation, radio waves, X-rays, all of it, is that actually light?
It's all the same fundamental phenomenon. Every single form of it, from radio waves that are meters long to gamma rays measured in like femtometers. It's all composed of the exact same unit.
The photon.
The photon. So really, to keep things simple and accurate, physicists will often just refer to all electromagnetic radiation as light, even when it's way outside the visible range. It's just light with different characteristics.
See, that challenges my intuition, though. If they're all fundamentally the same particle, why does their behavior change so dramatically? Radio waves just pass right through my walls, but visible light gets blocked by a piece of wood, and then suddenly, highly energetic X-rays can pass through my skin and bone again. It feels, I don't know, chaotic.
It's not chaos. It's all about structure. The deciding factor, and this is everything, is the relationship between wavelength and energy.
Okay, wavelength and energy.
That relationship dictates how much energy each individual photon carries. So a longer wavelength
equals lower energy, like radio waves.
Precisely. And a shorter wavelength means much, much higher energy, like with X-rays and gamma rays.
So how does that energy level translate into whether a photon gets blocked or not?
Well, whether light passes through something depends entirely on the material's atomic structure and that specific energy the photon is carrying.
Right.
So take the low-frequency end. A microwave photon hits an atom. It just doesn't have nearly enough energy to change the atom's electronic structure. I mean, it can't push an electron into a higher orbit.
So it just makes it jiggle.
It makes it jiggle. That's actually a perfect way to put it.
And that's literally how a microwave oven works, right? The low-energy photons are just exciting the water molecules, which generates heat.
Exactly. And if we look at scale, the microwaves in your oven might have a wavelength of, say, 12.5 centimeters. Now think about the metal mesh screen on the oven door.
Yeah, the one with the little holes.
Right. Even though those holes are huge for visible light to pass through, they're tiny compared to that 12-centimeter wave. So for the microwave, that mesh acts like a solid metal boundary. It just reflects them back in.
So the physics of getting through is entirely relative. It's about the wavelength size versus the internal structure of the material.
That really captures the core idea. Now, compare that with the other end of the spectrum, X-rays and gamma rays.
The high-energy stuff.
These photons are so powerful that when they hit matter, they can just blast right through structures that would easily absorb visible light. They carry enough energy to knock electrons completely out of their atoms.
A process called ionization.
That's the one. And it allows them to penetrate things like soft tissue, though they do get stopped by denser materials like lead.
So the key takeaway here is that for any kind of light to interact with matter, its energy either has to perfectly match an available energy state in the material,
or it has to be so powerful it just blows the electrons away.
You got it. Okay, so if a photon hits an atom or a molecule, what happens besides that gentle jiggling or heating? Let's talk about where color comes from.
Right. This is the core mechanism behind, well, pretty much all color, spectroscopy, and photochemistry. When a photon's energy perfectly matches an available energy state, the atom absorbs it.
And that bumps an electron up to a higher energy shell.
Exactly, a higher discrete energy shell. That's the electronic energy
That's
level.
fundamental jump.
Yes, but here's where it gets really complex. In molecules, which are, groups of atoms, these electronic energy steps aren't just simple stairs. Think of the electronic level as the floor you're on.
Okay.
Within that floor, you have finer, distinct vibrational energy levels. And within those vibrational levels, you have even closer rotational energy levels. It's like tiny shimmies of the molecule.
Wow, so it's energy stairs within energy stairs. It defines the exact, precise amount of energy a photon needs to have to be absorbed.
That's it. And when that excited state inevitably relaxes, that energy has to go somewhere. If it's released as a new photon of a specific wavelength, that's spectroscopy. If that energy difference is small enough, it might fall in the visible range.
And that's the color we see.
That's the color we see. Or if the energy is lost through those tiny vibrational shifts, it just dissipates as what we call heat.
And we learn that objects have color because they don't absorb that wavelength, right? They reflect it.
That's half the story. Most objects absorb energy across the spectrum, but it's the specific energies they absorb and then re-emit that determine the color. For instance, most inorganic metallic salts are super colorful.
Right.
That's because their specific orbital filling leads to lower energy differences that just happen to fall right into the visible spectrum for that absorption and re-emission.
Mm-hmm.
But, remember, everything above absolute zero is generating light in the infrared, just from having temperature.
That's a great distillation. So let's shift from absorption to the actual speed of light. We know it slows down in glass or water.
Yeah.
What's fundamentally causing that change in velocity?
It's a really subtle yet brilliant mechanism. Light is a self-propagating electromagnetic field.
Okay.
When this field enters a transparent material, its oscillating electric part causes the charged particles in the atoms, specifically the electrons, to oscillate.
So the light forces the material to vibrate at its same frequency.
Precisely. And this oscillation, this vibration, it isn't instantaneous. There's a delay. And this induced oscillation, in turn, generates its own secondary electromagnetic field.
Ah, so the material itself starts producing a wave.
Yes. And the original light wave and this new induced wave, they combine. They form a composite wave. And because of that little time lag for the material to absorb and re-radiate the energy, the overall propagation of this new composite wave is slower.
So the index of refraction, null or dollars, is just how we measure that slowing down.
It's the mathematical description of that lag. It's the aggregate effect of billions of tiny absorption re-emission delays inside the material.
So if visible light is fundamentally the same as radio waves, why is it so disproportionately important to us? I mean, what makes it special?
From a purely physical standpoint, it's not special at all.
Right.
It is, however, biologically and evolutionarily critical.
The spot.
Exactly. Our photoreceptor cells, our rods and cones, they evolved to detect this very specific range. And there are two main reasons. First, this range aligns almost perfectly with the emission peak of the sun's blackbody radiation. It's simply the most abundant energy source on Earth.
Makes sense.
And second, it's low energy enough that it doesn't instantly damage the sensitive tissues in our eyes. Unlike, UV or X-rays, which are ionizing and damaging, it's the Goldilocks zone of available energy that doesn't cause immediate harm.
Evolution is pretty smart. Okay, let's look at a major practical application of controlling light, trapping it, which is the whole basis for things like fiber optics.
Right. That relies on a principle called total internal reflection, or TIR.
TIR.
It can only happen when light is traveling from a high-index material, we call that the core, to a lower-index material, the cladding. If the light hits that boundary at an angle greater than the specific critical angle, it just can't escape. It's trapped.
And why does that difference in the indices matter so much?
Because that difference defines how steep the critical angle is.
Yeah.
The bigger the difference between the two indices, the smaller the critical angle, and the wider the cone of light you can successfully inject and trap inside.
So that's the numerical aperture you hear about.
That's the numerical aperture. For example, a tiny 1% difference in the index might give you an acceptance cone with a half angle of about 9.8 degrees.
So TIR is basically 100% reflection. But when light hits a boundary without TIR, like just hitting a pane of glass, is the reflection always the same amount?
No, not at all. It's highly variable. The amount of light that's reflected versus transmitted at any boundary is determined by something called the Fresnel coefficients.
Okay, the Fresnel coefficients.
These are complex mathematical tools because they don't just track the amplitude of the reflected waves, they also have to track crucial phase shifts.
A phase shift. You mean the wave gets flipped or moved in time relative to the original?
That's right. A negative coefficient, for example, means a 180-degree phase shift on reflection. And these coefficients are different depending on the polarization of the light, whether the electric field is oscillating parallel to the plane of incidence or perpendicular to it.
Wow. Okay, so managing all those phase shifts and polarization effects sounds incredibly complex. I'm guessing that's where physicists bring out the heavy mathematical artillery.
Absolutely. The need to handle waves and amplitudes and constantly changing phases all at once is why complex numbers are just indispensable in optics. I mean, trying to manipulate trig identities like cosine of alpha plus beta, one of the sources just calls it cumbersome and tedious.
Yeah, nobody wants to do that when you're modeling light traveling miles down a fiber optic cable.
Exactly. So physicists use complex notation, which is rooted in Euler's formula. E to the I phi equals cosine phi plus I sin phi.
Euler's formula.
It lets us represent these complicated waves way more efficiently using a complex exponential. It simplifies the math immensely.
So how does it simplify it? For someone listening, what's the trick?
Well, when you have waves, adding them with sines and cosines is messy. But if you represent them with complex exponents, adding waves often just turns into simple multiplication of the exponents. That expression, a cosine alpha plus beta, can be represented just by taking the real part of the complex number. It just compresses all that amplitude and phase info into one easy variable.
It's a convenience tool, but a really powerful one, especially when you realize how long ago physicists like Carl Friedrich Gauss were laying this groundwork.
The math is essential. It's the language of the field.
Yeah.
Especially when we get to the most mind-bending concept of all, the speed of light itself.
Okay, since we established light slows down inside a material, we have to talk about the really counterintuitive stuff. We sometimes hear that the index of refraction, 1 nullars, can be less than 1. That implies the phase velocity, the speed of the wave crests, can actually be greater than scalars. Does that break physics?
This is a classic point of confusion, and the answer is a definitive no. It does not break causality. The key is to distinguish between phase velocity and group velocity.
Okay. What's the difference, and why does one matter more?
So phase velocity, that's 5b day, tracks the speed of the individual rapid oscillations, the crests of the wave.
Right.
And in some media, yes, phi lots can exceed c dollars. But the group velocity, phi d doll, that tracks the speed of the overall waveform envelope, the packet of information itself.
So the group velocity is the speed of the actual information, the energy, the thing that can't break the speed limit.
That is the core insight. Phi dollars is associated with the propagation of intensity and energy flow. And the fundamental rule is that the speed of information transfer, the energy packet, must never exceed c d dollars. So the group velocity never exceeds c dollars. Causality is preserved, even if the individual wave crests are moving faster than the beam itself.
That distinction is genuinely profound, that the crests can move faster than the energy envelope. It solves that whole paradox.
It does.
Let's quickly pivot to how we measure light and actually see color before we wrap this up.
Okay. When we measure light, there are two distinct fields. First, there's radiometry. That's just pure physics. It quantifies electromagnetic energy power per area, like watts per square centimeter.
And the other is photometry. That's the human element, right?
That's the human element. Photometry adjusts that raw radiometric measurement based on the human eye's very specific wavelength-dependent sensitivity. We just don't see all wavelengths equally. Our eyes use rods for dim scotopic vision and cones for brighter photopic vision, and they peak at different wavelengths.
And color, as you said earlier, isn't simple.
No, color perception is inherently a three-dimensional vector space. That's because we have three types of cones: short, medium, and long wavelength sensitivity. So you have to quantify color based on the subjective response of those three cone types using what are called color matching functions. That's how we got models like the CIE 1931 XYZ color space.
Okay, last thing. Let's touch on how light spreads out and limits what we can actually see, like in a telescope.
That brings us to diffraction. And to understand that, you first need to understand temporal coherence. It's basically a measure of how long a light packet is uniform in phase.
Okay.
You can see this in interferometers. The signal eventually just becomes steady when the time delay is too long for the waves to interfere. That means low coherence. The broader the spectral width of the light, the shorter its coherence time.
And how does that connect to resolution limits?
Well, diffraction is what limits our ability to resolve small details. Fraunhofer diffraction is the maximum amount of spreading a wave shows when you look at it from really far away, the far field limit. And here's the crucial part for an instrument like a telescope. A lens doesn't just magnify. It conveniently images that far-field diffraction pattern directly onto its focal point. And that fixed pattern is why diffraction fundamentally limits the resolution of any optical system, no matter how perfect your mirrors are.
Wow. We have traveled from the fundamental photon-wave duality all the way through the atomic mechanisms of color and refraction and landed on the mathematical framework that makes sure the universe's speed limits are obeyed. It's been a massive dive.
It has. And we ended with that crucial realization that group velocity tracks energy and has to stay below 2 hours. But to build on that, we need to look at what happens when the refractive index isn't just a simple real number, but a complex value, $+ plus $kappa.
And that imaginary part, what does that do?
That imaginary part, kappa, it accounts for energy loss or gain in the medium. And both null and kappa are highly dependent on the frequency of the light.
So why does that frequency dependence change the physics?
Because when a pulse of light hits a medium, the material doesn't respond uniformly. It responds to the instantaneous power spectrum of the pulse. This means the material can actually treat the front of a pulse differently than the back of the pulse, which leaves you with an important question to think about. If the speed of information is definitively tied to group velocity, how exactly does the material's structural response to that instantaneous power spectrum determine the ultimate speed limit and the limit of causality for light passing through it?
It's proof that even at light speed, structure determines fate.